But okay, so yeah, there are a few announcements. Our club, we are a security club at University of Toronto. We primarily do a year-long CTF, but we're also hiring for roles, year-round roles. So if you're interested in helping out on the CTF development or helping up setting up finance, we're hiring for those. There's going to be no workshop in the final season because we're going to be studying for finals. So we might have another workshop in May, probably around blockchain security. But I can't promise. There's going to be something in May though. And we're also going to be setting up a CCNA study group. So if you're interested in studying for networks, computer networks, getting a certificate, it takes a long time. It takes like 1 year, but we can probably do it a little bit quicker if we are dedicated. But if you're interested in studying for the CCNA, you can send me a message as well. Yeah, okay. Also, there should be some chocolate here. This is okay. If you want chocolate, there's some here as well. But yeah, today's going to not go too deep into forensics. I wanted to cover a little bit about disk forensics, about copying entire disk drives and then going deep into them. We can probably look at a few challenges, but we're not going to go too deep into disk forensics. We're going to cover file forensics, steganography, which is the practice of hiding things in files, network forensics, some system artifacts and logs, and certain things that you're going to be looking for when you have a Windows device, and memory forensics. So forensics is the process, if you're not aware, it's the process of collecting artifacts from computers that maybe have been compromised. Maybe they're a suspect's computer, you're part of a digital forensic investigation, maybe you are part of the police and you're collecting data off of someone's drive. So you're looking for things that are artifacts, and artifacts are pretty much anything that involves user activity or human activity or something that you're trying to prove. Maybe it's something relating to malware, it's logs, you can look at logs, you can look at packet dumps, memory dumps, and files that have been collected previously as well. So that's what an artifact is, and that's your main goal when you're collecting and you're doing digital forensics, is to find these artifacts. So we're going to go into files first and how you can look into files, how you can analyze files. The main idea is that you're going to be looking at a variety of files, so you want to be good at learning file formats. And file formats are just the way that files are structured. Files are just a pattern of bytes, but they're structured in certain ways that make it so that the software that reads the file is able to extract the information. So sometimes files have different encodings, they have different compressions. So the file format is the thing that defines that. So we're going to cover one of these file formats. A lot of them are defined in RFC's, request for change documents, and a lot of them go through revisions. So if you can find a technical specification, that is probably going to be the main source of truth anyways. So there's a file command on Linux, and the way that it works, it's really good for analyzing and like telling you what a file is. So if you run file and then file afterwards, so file and then your file name, it can tell you what sort of file you're looking at. So on the left here, I have a PDF, and I can dump the bytes with XXD, and I can see the first few bytes. And how file works is that a lot of files have this thing called the magic bytes or magic numbers. These are symbols specifically for the file that are shorthand. They're like very unique. They're unique to the files. So in PDF, you have %PDF and then the PDF version. So that is a magic number, and then there's also the version afterwards. If you mangle that, so if you change the first few bytes of the PDF file, the magic number is no longer the same as %PDF, so the file command doesn't work. But if your file is usually non-corrupted, if it's just a normal file, a file that you got maybe from the internet, from a TCP, something reliable, and you got the file there, the file is not damaged. Usually what we do is we check with a checksum if the file is damaged or not. But if it is good, then you can use the file command and you can see exactly what the file is. So in this case, the file is a PDF document with version 1.6. So it's a really good command to run on Linux systems. Yeah, so we'll go on to an example file, and the file that we're going to look at is a very simple one. So it's the PNG file format. The PNG file format is comprised of a header and a collection of chunks. So the header is a lot of information, a lot of metadata. Some things in a header are just used for compatibility. So we're going to look into the actual bytes of a PNG later on. But some of them, like the CRLFs, are for compatibility across different devices. There's things, metadata about the header, metadata about the PNG, like the width of the PNG, the height of the PNG, the color type, the compression, if there is compression, and then there's also something called the CRC, which we can get into later as well. And the PNG is also comprised of chunks. So chunks are the data that comprises of the actual PNG data, like the RGB pixel data. So that's what the chunks contain. And the chunks have a length of the chunk, and then the type of the chunk. It can either be a data chunk or an N chunk or something else. And there's also the raw PNG data. I think it went back. Okay. But yeah, we'll look into the actual bytes of the PNG. Still recording. Okay. Yeah. So this is an example. This is if you have your PNG. Oh, sorry about that. But yeah, we want to look at the actual bytes and we want to map it back to the file structure. So yeah, so in this example, you have the actual bytes here. This is represented in a hexadecimal. So the first, let's say 16 bytes are the PNG header. And then the next 8 bytes are the length, and the next 8 bytes is the I header. So this would map directly to the header. The header is comprised of the header length, so the length of bits in this section right here. So if you take a look at the length section, you can actually know how big the header is. The next section that you'll find is the chunks, and the chunks would contain the chunk type, which you can just decode directly. So this would just be ASCII. This IDAT segment would just be ASCII. And then there's also the chunk data as well. The chunk data is comprised of the RGB values of the image, and there's a CRC at the very end. So that's an example of mapping the actual bytes. When we go on later on, we can open up a hex editor and actually dissect the image data, and we can actually see it highlight a few of the bytes and then back to the original file structure as well. So how can we abuse the file formats? Well, the way that the PDF image parser works is that it would look specifically at the header, and then from the header, it looks at the next chunk, which is directly after that header assumed. So once the header ends, the very next byte is the start of the next chunk. And after that, it continues reading the next chunk, until it reaches the I-end chunk. So remember, in the chunks, there's different types of chunks. There's the I-data chunk and there's the I-end chunk. The I-end chunk will be the chunk that is in this image. Anyways, you can see the I-end chunk is the very final chunk. So what you can do is you can put data at the end of the file, so after the IN chunk, and then the PDF image reader will not read that data, so you can hide some data there. You can also do some steganography techniques, which is just doing some things with the raw payload data, so not actual file metadata, but the actual data of the image, and you can hide some data via steganography techniques, which we'll talk about later. If you want to know if a PNG is normal, you can use PNG check as well, which is a tool that you have to install, but it should be cross-compatible. So the CRC checks. So if you're interested, a CRC check is a small hash, and the reason why we use it, it's usually a fixed size, but it's not meant to be a cryptographic hash, it's meant to be an error detecting hash. So the basic idea is that you're using the actual values of your CRC to detect if there was an error. One common way is to check against the parity. So maybe all of the bytes in the CRC should be even for there not to be an error. So you'd be using the CRC check to check if there is an error. And some versions of the CRC allow you to correct an error afterwards. So you would use the data in the CRC and do some manipulations on the data to recover the original data that was damaged before. So something that you can do if you have enough samples of the CRC is you can find the original CRC algorithm. So you can produce new CRCs from different data. So This is something that you can do possibly in an attack scenario to spoof some data so that it wasn't seen to be corrupted. Okay, we'll go on to the next one, but that's very important. You're going to see CRCs a lot in network traffic and also just in files in general. So again, magic numbers, these are just collections of bytes. There are so many magic numbers, so almost every single file has a magic number. So for example, in PNG files, you have the .png. These are the first few bytes of the file. The PDF files, you have the %PDF, and then for P files, you have the MZ bytes. And it's just ASCII as well. So another important file is a zip file. And it's important to know a variety of different file formats just so you have this intuition of how to read a file and then map it to a file format. And it's also kind of cool. So the zip file format, the way that it's read is that it actually looks at the final, so that the very end of the zip file first. So the end of the zip file is the end of a central directory, and it points to things that are stored up here. So the records are the actual files, and they're the compressed files, and then the dir entries are the metadata and folder structure of that file. So dir entry 1 corresponds to the file metadata and the directory data of the first record, and the first record contains the compressed file data. And the file data is usually compressed with the deflate algorithm, which uses Huffman encoding, but we don't have to go into that. It's just a really good compression algorithm. So yeah, we can look more deeply into how it could work. So you can zip up a collection of files, and then how it will look like in the very end is you have the records, the number of records corresponds to the number of files that you have, except for the very first record, which if you are zipping a directory, then the very first record would be the empty directory file. And then you have the entries corresponding to the records. So some of the things that you'll see in a record are the record header, which contains the CRC, the file name, the file length, and then the compressed size. And then you have the compressed size, which is the compressed data inside of the record. And because you looked at the header, you know how big the compressed size is in the end. You also have the directory entry, which is comprised of a collection of metadata about the file. So you have the MAC times, modified access create times, and then the compressed and uncompressed sizes. And then you also have the end locator. So the end locator is going to be used later on to actually find the first directory entry. So we'll actually go into how the zip files are parsed. So everything is dependent on the end. So the end of the central directory is used to find the first directory entry. And once you find the first directory entry, it has a pointer to the first record. And then you can read that record data, and then you can unzip it by, depending if there's a password on the zip or not, you can just unzip, uncompress the deflated file as well. So again, it looks at the end of the file. So what you can do is you can abuse this file format. So one of the things that WinZip does is it creates self-extracting zips, which makes the first few bytes of the zip file executable that will unzip the zip automatically. You can also stuff data between each chunk because the actual records are pointed to by the directory entries. And then you can also change the end of the directory to just hide some files, because the way that zip would look for the files is depending on the end of the central directory. So if you just say that there is 2 files instead of 5, you can hide some files in that regard. So this next. Yeah, again, this is for password protected ones. Yeah.
I'm a little confused, like what a directory entry is.
So yeah, so directory entry is, it has a lot of, okay, so it has the structure of the file. So it has the directory, which directory the file lives in, and then also some extra data about the file. I don't remember exactly what it contains. We can go back, but we can look through it in the hex editor later on.
Right.
but it has more metadata. It has it has the modified access creation time of the file as well. It has a bunch of metadata that shouldn't be in a record. Um, to be honest, I don't know why it's split up. It could just be put in the same area, but it's just extra metadata about the record. Um, yeah. So I guess essentially this first segment is just about file format. So we'll go into later things like disk images and memory dumps and network forensics later on. But it's important because there are certain things that people can do with files that just seem like magic, and you have to understand the file format in order to disentangle that. Okay, one more file we're going to talk about is a PDF file. A PDF file is comprised of a header and then a bunch of objects. So the header contains a magic number and then a PDF version. An object contains the actual structure of a PDF file. So the structure of a PDF file is comprised of maybe booleans, integers, real numbers, comments, names, and then also streams. So streams are the actual bytes data, like an image or a zip file or like a program. These are the actual bytes, and they are encoded within the stream. So the stream data is just a collection of bytes. And then you can also reference other objects. So you can reference another image, and then you can say perhaps this is the name of the image in another object. So you can create references of other objects as well. And at the very end of the PDF file, you have a reference table, which has the reference numbers of your objects, and it maps them to the actual offset, so the actual location in the PDF file. So it is just comprised of these objects, and these objects are just this type of data. You also have dictionaries, which are used sometimes in locating images, or actually, yeah, pointing to images. There's comments. Actually, a lot of this stuff depends on the tool that you use to generate a PDF, but your main goal is to look at the streams anyways. The streams are the actual contents, like the images or the font files or the code. So maybe we can look at an example. Okay, I don't know why the slides are so slow. Okay, anyways, yeah, so you can open up a PDF file and you can actually see that it is defined by this raw plain text. So the stream would start, and then the data in between the stream is the actual stream bytes. So you have to decode that. You could like rip it out with a hex editor, so just rip out the intermediary segments between the streams. You could use other tools. So there's another tool that we can talk about later on that would uncompress and then make it so that the PDF is easier to read. And yeah, so an example of PDF artifacts. So PDFs are just collections of objects, right? So if you add a new object, like a black box, to hide something, well, you still have the original text underneath. So you can just remove the black boxes, which are just objects. You can remove those in the original file, and you can find the original text. So this is not very good if you're trying to censor anything. And you can also, if you want, you can use PDF to text to just extract the underlying text of a document as well. So I think the next one is an example on how to uncompress. So uncompressing a PDF would make it so that it's more human readable. So originally the original image that we saw, the PDF was very compact, but if you uncompress it, the objects are easier to find, and you can rip out an object directly when it's uncompressed. And yeah. There are a few more file formats. So there's a few more file formats that are important to talk about if you plan to do anything like malware analysis or any sort of reverse engineering. There's the P file format, and then there's also the ELF file format. So these are executable. They're meant to be executable. So they have a lot of sections about how memory should be laid out and where specific program structures are, where libraries are located, where variables are located. So you can look into the reverse engineering seminar that we did about a month ago if you want to learn more about these file formats. But sometimes you're going to find these file formats maybe downloaded in a network capture or anything like that. So if you want to actually play around with a file, because a file is just a collection of bytes, you want to be able to map that back to the file structure. You can use something called a hex editor. So there are a lot of very good hex editors, but you want to find one that understands the structure of files and is able to highlight them as well. So you can use 010 editor, which should be free. It has a free trial, and that one is pretty good. So we can use that one when we're actually doing the demo parts. There's also evil files. Evil files in a sense, well, they're not evil, but these are weird files that have multiple formats. So maybe you open a PNG, or maybe you open a file in a PNG viewer and it shows a PNG, but then you open it up with like a PDF viewer and it shows a PDF as well. Or maybe you can unzip it and then it also has files inside of it and it unzips like a zip file. So these are files that abuse the file format to contain different sorts of files by themselves. If you want, you can view exactly what file signatures or what file magic numbers there are recursively with this file command file-k. An example of a polyglot that you'll see sometimes that we have in the small workshop is embedded file. So usually, I mean, in a PDF, you have embedded files, right? You have images inside a PDF that are compressed, but you can also have any sort of file that contains another file. So maybe you can stuff a JPEG, a PDF in a JPEG, and you can stuff a zip in a PDF file. Some example of how you might want to do this is you could use StackHide, which is a program that is able to embed another file inside of PNG and JPEG images. Actually, I think it's only JPEG images. So you can hide any file inside a JPEG image, and then it would be hidden, and you would have your own key, and you could extract that hidden file based off your key. But how practical is it? It kind of is practical if you don't really have a good way to detect it. Yeah, some exploits in web exploitation, if you are sending data and they have a misconfigured MIME type, or maybe ways that they parse the file, it could be problematic if you have files with multiple formats. And that is also a type of malware, polymorphic malware, that is able to change file type. But okay. We'll talk about file carving, and file carving is the process of extracting these embedded files from a file. So what you could use is Foremost. Foremost is a tool that is able to automatically recover these files. So just trace through your file and then try to find the other file signatures and then extract based off of that. So you can install it on Linux systems. I don't know if you can install it on Windows, but if you can't, then I'm pretty sure Binwalk is also installable, and Binwalk does a similar thing. So Binwalk is going to walk through your entire file and then find any file formats that are similar to something else. And these are automatic ways to carve a file. If you want, you can also do it manually using the dd command. Okay, so we'll do a small challenge now. If you want to install a file and then try to carve out segments as well. So we have a challenge here. I'm pretty sure it's public. You can try out the challenge. It is comprised of a file that has many files inside of it. So maybe I'll give you guys about 5 minutes to take a look at that, and then we can come back and I'll show you the solution. I'll open this up. So I have a hex editor on my system, and I can open up the PNG in the hex editor. Okay, so the hex editor is able to highlight specific segments of the data. So it's able to see the entire first header and highlight that. And then it says the second chunk of the image is located here. I wonder if I have the tool PNG check. I might not. So obviously there's something wrong with the image. Oh, okay, never mind. So if you run PNG check on the image, it's going to say that there is something at the end of the PNG file. Actually, if you look at the PNG file, it's actually quite large. So there's something that is wrong with the PNG file. What I'm going to do is I'm going to move this PNG, I'm going to move it into the Linux section. Okay, sorry the computer is so slow, but I hope you get the idea. So there's something at the very end of the PNG, and we want to extract that out. So at the very end, where there's an IN header, okay, whatever. At the very end, where there's an IN header, oh, okay. So there's something at the very end here, and this is kind of just it. Right, this is one chunk, this is one chunk. SSD, challenge, PNG. Okay, well, you'd have to use a hex editor to find where the IN segment is. But we can use an automated tool to carve it out. So there's foremost, which would take your input and it will look for any embedded files into it, and it would output the files that are found. So it would output it into a directory. So if you want to run a command, it's foremost the input and then the input file, and then the output is the folder that you would output at. So in this case, we found a PNG, which was the original PNG, but we also found a zip file. And if we look at audit, you can find that there were two files extracted. There was a PNG and there was a zip. So if you look at the zip, this is a zip file. So if we want, we could look at the actual hex data of the zip file. We could also do a raw dump of the zip file. There looks like there's a file inside of here, a PDF file that it found, but we have to take that out. So you have to unzip the zip file, but it requires a password. So the password is actually inside of the metadata of the image, but it's inside of metadata, but you can also find it, there's also a second one inside the actual image. If you just looked at the raw bytes, you can also see the password for the zip here as well. So if we go to dump and we go to zip, and then we can input the password and you get a PDF. So this is a PDF. You can open the PDF in a text editor to get a general grasp of it, but it's not going to be decodable. You can, do I have a key PDF? Okay, I might not, it's okay. If we open up the PDF, there's going to be something that's blocking the flag. Maybe it renders it different. Okay, so there's this box and we need to remove the box. What you can do is you can extract all the files from a PDF. So I think it is PDF images. Okay, you can install that. There's a tool that you can install. It's called PDF images, and it would just extract all of the images from your PDF. Okay, I have to find my password really quickly. Images. F. PDF file image roots. Okay, so there are two images that we extracted, and where are we? Oh, okay, yeah, that seems right. Okay, so those would be the images. Okay, yeah, so the images are here. Okay, I don't know why it's so slow. But essentially, the entire challenge was there were embedded files. You could use Foremost to carve out a zip file, and then the zip file contained a PDF, and a PDF had a collection of images within it by default. And you could use a tool like PDF images to extract the images. So what are these images? Okay, this is one image, I think. Okay, and this is the flag. So that was pretty much the challenge. I'll go a little bit faster for the second half when we talk about. Actually, how much time do we have? Okay, so I'll go a little bit faster, and then we can stop maybe about halfway through. Yeah. So for the first one, it was Foremost. Foremost does it automatically. So Foremost I. Foremost I for the input file, and then the output is the folder. Binwalk also does a lot. Yeah. Okay, we'll finish off this section about files, and then we'll take a break, and then I'll see if I can get some food. So the other thing about files is that they usually have metadata, and metadata can be embedded within a file, or it can be stored inside of the file system as well. So metadata includes things like location, access times, or file size. It depends on the metadata that you have. But for images, by default, they would record things about the camera. Sometimes if you enable it, it can also record location, like the latitude, longitude of the image as well. Okay, we'll go on to the next one. So yeah, so there's embedded metadata. So this is metadata that's inside of files. A very common one is EXIF metadata. So this is for images and videos. XMP is also a common one that is in images and other video formats, GIFs. IPTC, MXF, ID3. There's so many more formats, but you're going to be seeing EXIF a lot because most files, videos, audio have an EXIF metadata embedded within them. So EXIF actually reveals quite a lot of things. EXIF reveals camera settings, it reveals GPS, date and time. This is a funny image that I found online with some people with guns, and you can see where they are, the longitude and latitude of them. But yeah, it's compatible for video, audio, and images as well. Social media sites often strip this data. because you don't want that anywhere. So a good tool is EXIF tool. EXIF tool allows you to actually see the metadata of files. So you can install it on almost every single operating system. Well, it's written in Perl, and anything that can run Perl should be able to run this. So if I run it on an image, you can see some things about the access times, some things about the MIME type, the operating system that took it, which is Windows, and depending on if it was taken with a camera, so in this case it was, you can see some things like the resolution units and stuff like that. There's also file system metadata, so this is metadata that's stored on a file system. So for Linux file systems like ext4, usually they use something called inodes, and in Windows they use something called the MFT. Actually, Windows has their file metadata scattered all throughout the file system, but the MFT has a lot of the data that you want. So in ext4, ext4 has things called inodes, which are things that store the file. So they actually store the file directory, and then they store things about the file, like the permissions, the modification and accessing and change times, and also the owner of the file. And they also have blocks, which point to the actual raw data stored on the disk. So the raw disk, the disk data of the file as well. If you want to read the actual metadata of the inode, you can use the stat command to read it. We're going to talk maybe a little bit about access times, because I guess it's kind of relevant. There's a little bit of nuance of it. So access times are not always to be trusted. There's modify time, which is whenever you change a file, the modify time changes to the exact time. And it's all in the Unix timestamp, but yeah, it changes to whatever Unix timestamp that you modified it at. There's access time, which is every time you access and read a file, but usually this one is disabled by default because you're reading files very often, especially on system files, and you don't want to change that. That would be a lot of writing, because you have to change the access time every time you read a file. So that is very expensive. And there's C time, which is whenever the file's metadata is changed. But usually these things are not that important. I guess the most important one is modify time, but the other ones you can't really trust them in all cases. Yeah. There's also this other thing that you can do with metadata. It's very common in macOS, so macOS actually uses it a lot. But in Linux, you can also do something similar, which is extended attributes. So for a file, you can set up custom metadata. So you could set up a name and a value pair. Usually it's used for access control lists or file hashes of the file as well. So this is something that's very common in macOS. macOS automatically creates these. On Linux, usually you have to set your own up, or maybe some specific programs would set their own extended attributes as well. So yeah, so I think that's everything we had to talk about for files. We'll take maybe a 10-minute break here, and then we'll go into stag and network stuff. So we'll take a break. Essentially, what it is it's the practice of hiding data within other data. So usually it's done with images or audio files, but it's the idea of hiding other data within data. So you have like a picture here, and then you can embed text into it. This is not the same as metadata because you're actually modifying the original payload data, the actual data of the image, not the metadata. So there are a few ways that you can go about doing it. For images, there's a lot of ways. One way that images store data is they store their color data, and they do it within the pixels. So pixels are RGB, and what you can do is you can separate those RGB values into the corresponding bits. So this is obviously a single byte. So a single byte turn it into the bit version. You have 8 bits. So what you can do is you can split your image up into a single one of these bits and then represent data like that. So there's a technique called least significant bit steganography, and it abuses these bits. So we're going to create a bit plane, And how you create a bit plane is you pick one of the channels, red, green, or blue, and you would pick a specific bit in that channel. So let's say the second bit of the red channel, and you would only use that. So if you represent your image as a matrix, and it's a matrix of RGB values, and you wanted to create a bit plane of the red value, you only get the bit for the red channel, and you only get the second bit of that. So this is an image representation of a bit channel, and you'd create a different matrix like that, essentially. So you can create a different image like that. Something that you can do is you can hide images or hide data within the lower bits, because that actually doesn't change the image a lot. So this is the original image, but the original image has different bitmaps for the green layer. So the green layer, the second bit for the green layer, the original image doesn't look that bad, but if you get only the green bits, you can see that the data in there is completely separate. It's like the R1 bitmap is the normal thing that you would see, and then the green 2 bitmap is the thing that I modified. But you can see that it doesn't really impact the original image a lot, because it's only the lower bits of the green channel. That doesn't really change the green in the image a lot. So this is one method of steganography. You don't have to make it an image. You can change the bitmap and then just make it text as well. That's another way, but that's the basic idea, is you are modifying the lower and least significant bits inside a bit plane. So that's one very common steganography technique, especially for images. There's a lot of techniques when it comes to images, I guess, because, well, it's a matrix, and I guess it's very easy to hide data in images. There are some tools that you can use to browse the bit planes. So Steg Online is a tool that you can use to browse bit planes. A Parasolve also has a variety of least significant bit tools, and a Parasolve also has a lot of file carving tools and automatic file recovery. So the things that we did with binwalk and foremost, and looking if a file has different files inside of it, a Parasolve can also do things regarding that. There's a different kind of steganography called subpixel steganography. So when you look at your monitor is actually a collection of red, green, blue tubes, but they're very close together. And this is called a subpixel. So every single pixel is red, green, blue channels. And your monitor, when you look at it from afar, you can't really see them. But if you take a camera, a very high fidelity camera, and you zoom in enough, you're able to see these subpixels. And so these are specific images that abuse the subpixels so that you can represent messages. And so there's a software online, I believe, that can create subpixel steganography tools, and you would have to take a camera and actually zoom in to see the original image. So that's one more sort of image steganography technique. You can hide some text in there. For audio, you can hide data within spectrograms. So for a waveform diagram of audio files, you can create it, you can change it so that it displays a shape. So in this case, you can have text within the waveform data. Obviously, the audio data is going to sound horrible, but I guess this is sort of thing that you would include just for the sake of having an image. None of steganography is totally practical. Steganography techniques are not really designed to be that practical. They're just a branch of cryptography that is kind of interesting, and you might see them a lot when you're doing forensics challenges, especially least significant bit techniques and spectrograms. There's another technique for radio and waveform audios, which is called slow scan television. So this is an actual protocol that radio operators use to transmit images, and the images are not very like they don't really keep their quality, but it's a way to transmit images, and you can convert your waveform files, your WAV files, into these images with the SSTV protocol, the encodings. And there's also a tool QSSTV that you can use to decode it as well. And here's one more thing that you might see. It's not really steganography, but it is a way to encode information. For any sort of picture that you print out with a laser printer, you're going to have metadata about the printer that was originally printing it. So why is this useful? Well, if you print a document like a counterfeit dollar, the police can actually look at the yellow printed dots and backtrace it back to the original printer that printed it out. So this is an encoding for creating these sorts of machine identification codes. And you can only really see these yellow dots under blue lights. But this is kind of something that's interesting that can be used to show a specific device. Okay, so we'll go into network forensics now. Network forensics is a bulk of the challenges that you'll see. It's either going to be steganography or files or network forensics or maybe even a disk drive challenge. But network forensics are some of the more fun ones. So we're going to go over a brief recap of computer networks. A computer network is just a bunch of protocols between a hardware and a software that allow for communication between two computers. And the networks will depend based off of how the computers are talking, if they're in a local environment or if you're communicating all across the internet. So we'll go over a few protocols and then also a few network diagrams for the local internet and the WAN as well. So in terms of packets and protocols, you have packets, which are the units of data, or they're also called frames. So packets and frames, which are the raw units of data, and they're encapsulated by the headers of other protocols. Encapsulated by the headers or footers. So in terms of TCP, TCP adds a header in front of the data. In terms of IP, IP adds a header in front of the data. So we'll talk about these protocols later on, but the idea is that you are encapsulating the data with other metadata about that data. So an example of packet data that can be sent through the wire is this. So this is just a raw collection of bytes. You have your Ethernet header, your IP header, your TCP header, and any of your payload. So when the actual message is being sent across the wire, you would first have to take apart the highest level header. Okay, we'll see. Anyways, you have to take apart the highest level header, take that out, and then you're left with the data at the right side. And then you would take off the IP header, and then you're left with the TCP header. And you take off the TCP header, and you have the actual payload. It comes down to the OSI model. So the OSI model is this category of protocols and what level they should be. So the protocols are created for different levels. Some of them are for the lower level actual ways that you transmit data across the wire. So the Ethernet protocol or the Wi-Fi protocol. There's the network protocol, which talks about how you should address things and how things should be communicated on at the network level. So a very important thing is the IP protocol, which gives things an address. There's the TCP protocol, which allows things to have sustained communication. So it's how data should be transported, whether it is fail-safe, so it allows the data to be completely intact when transferring, or if with UDP, you don't care if there's data integrity, you just continue forwarding it. And then there's higher order protocols like application, presentation, session that are going to be used for specific circumstances. So presentation, usually what you're doing is you are changing the format, maybe you are doing some encryption on the data, and there's application which are specifically being used by applications like HTTP or SSH for specific applications like a website, web browser, or SSH clients. So I think we're going to talk about a few of these protocols. Before that, we have to talk about a network interface. So the actual way that you communicate with a network is through a network interface. These could be physical or they could be virtual. And for the physical interfaces, you usually have something called a MAC address, which is the hardware address that is given by your manufacturer. So you have your original manufacturing code, and then you have your unique identifier for your specific device. Set to the MAC address is, you'll see it sometimes on your physical hardware card. It's imprinted by the manufacturer, so you can't change it, but you can spoof it if people ask you for it. But you don't really have a good reason to do that. Anyways, network interfaces, if you want to see them all, you can run a few commands. You can use ip-link show on Linux, you can use ipconfig on Windows, and you can see all of your network interfaces. The reason why you want a network interface anyways is to connect to the internet. So the physical hardware cards are the ways that you connect to the internet. Some of the technologies they use are for Ethernet, they use RJ45, that protocol, that wire, and then they use antennas for 802.11 for communicating via Wi-Fi. So if you take apart your laptop or your actual computer, you can see the cards with the expansion ports. So yeah, how it works is that you have your physical interface and it's sent to your network interface controller, and that's sent to your CPU for processing. So the lower level protocols, like the Ethernet protocols, are sending it through the wire, and then it's decoded by your controller. So there's a few modes that we can talk about when it comes to network interfaces. For managed mode, the only traffic that you can see are the traffics of your own MAC address. There's promiscuous mode, which would allow you to look at all of the packets regardless of MAC address. So in a wireless setting, right, you can just hear all of the packets in a wireless setting. But normally, you only care about your own. You only care about the packets that are coming to your MAC address. So by default, we are working with managed mode. But if you want to capture the packets that other people are sending, you can use promiscuous mode, which would pick up all of the packets regardless of the destination MAC address. And if you want the ability to capture the rawest frames that are being sent across the network, so you want the actual raw frames, the raw Wi-Fi frames, you can set your network interface card to monitor mode. So these are separate modes that you can use. When we actually do packet capture, we have to do it in promiscuous mode or monitor mode, because if we don't, then we're just seeing our own traffic. So that's the basic idea. Maybe we'll have time to look into how Wireshark works later on. But yeah, so in terms of network architecture, there are a lot of ways that you can connect computers together. If you want, you can just strangle a wire, like connect a wire between the two, and then you can directly communicate. You have to set your own IP addresses, but you can directly communicate peer-to-peer network by just connecting a wire between them two. You are able to connect things in a LAN, so you have a switch, and then you connect devices to the switch, and the switch would take in your traffic and forward it to the other devices. So that's for small homes and offices, or just local networks. They're going to be using a switch for the most part. And then you have a wide area network, which is comprised of using a router, and then your router would forward the traffic across the internet to another router that has your target device that you want to communicate with. So the way that the internet works is that it's just a collection of routers, and the routers would use, yeah, so that is a wide area network. So these are kind of the types of networks that we'd be looking at mostly. There are different networks like mesh networks, but we don't really have to go into it. Some of the things that are most important that I guess you've probably seen before are internet protocol and the addresses that are related to the internet protocol. So there are two types. There's IPv4 and IPv6, and they just have different formats for the internet addresses. So IPv6 has a lot more addresses than IPv4. There are public and private IPs. So the public IP is the IP of your entry points to the internet, so your router, and then your private IP is the IP for your device, so your local device that is inside of your local network. And you can find both. You can go online, you can find your IP through the internet, for a website that looks at your router's IP, and you can find your own IP for the IP commands. And in terms of what actually constitutes a private IP, well, it is divided into different classes of IP ranges. So I guess very commonly, we're going to be using class C, but it depends if you're using class B or class A. In class C, you'd be using the private IP range between 192.168.0.0 to 192.168.225.225. But there's also different private IP ranges depending on the way that your network is structured. So the actual raw bytes, what's being sent across the wire, is dependent on the IP frame. So this is the heart of the IP protocol, is the IP frame. There are a few things that you might want to pay attention to. So there's a source IP and a destination IP. And so these are just the IP numbers. They're 32 bits long. You can also take a look at the time to live segments and the R, DF, and MF, which actually, no, that's not that important. It is like okay, we'll talk about that later. It is a way for IP to break up packets into smaller ones. But source IP, destination IP, time to live protocol as well, and then some other options. So yeah, so we'll talk about it now. So IP fragmentation is this idea of splitting up your messages into smaller messages, and this is dependent on the maximum transmission unit, and it is something that the RMF flags are setting in the IP header as well. So for example, if your maximum transmission unit that your other device has is 2,500 bytes, then you have to split up your message into two messages, and then the two messages have different sizes. So that's that basic idea. There is a different protocol, I think. We might go into TCP. Yeah, so TCP is the way that you actually communicate data between devices. So it ensures that data is being sent in the correct order and that data is not being lost. So how it actually works is it is still a header. So it's a header for your packets. Your packet data is after the header. So what's important to know is the source ports, the sequence number, the acknowledgement number, and the destination ports. And there's a few flags as well. This CWR, push, SYN, FIN flag. So the ACK, push, SYN, and FIN flag are kind of useful to know. Maybe the reset flag is also good to know as well. But the heart of the protocol actually depends on the sequence number and the acknowledgement number. So we'll go into how it works. First, how it works is that you have to establish a three-way handshake. So you have to send a packet with the SYN flag on. So if you remember the header, there's a flag for SYN. You have to enable that's turned on. And then the recipient is going to have to return with the SYN and the ACK flag on. And then you have to acknowledge with the ACK flag on. And what you're sending between them is you're sending something called the initial sequence number. And the initial sequence number is something that you set within the header, and this is the starting number that you guys use for your communication. So A generates a sequence number, and then B generates a sequence number, and then you use that to communicate with each other. It is like a random value that is used to ensure communications are unique. So this is an example. You have generated a random sequence number, and then you send the requisite flags. So you send a SYN flag, and then they give you the SYN ACK flags, and then you send the ACK flag as well. And now you guys both have the initial sequence numbers. So yeah. So now that you have the initial sequence numbers, you can initiate a communication. And the basic idea is that you would be able to send the data. And when you send the data, you want to send a sequence and an ACK. So sequence is the number of bytes that you sent. So it's the number of data bytes that you sent to the other person. And an ACK is the number of bytes that you received. And you want to ensure that you are incrementing your seek every single time that you're sending it. When you do that, the recipient would check, verify if the amount of bytes that they received is the same as the seek that you gave them. If it's not, then they can ask you to resend the bytes as well. If they're sending you some data and the seek that they give you is not correct, then you could also request, or you could do something on your part to tell them that they haven't sent everything your way. And ACK is the number that you've received as well. So if you send something and they received So if you send your ACK and then they have more things that they sent, then they know something else is lost as well. One way that we actually send these packets back and forth is called delay acknowledgement. So when you're actually looking at the packets, it's not just back and forth, back and forth. Usually it's sending 2 requests and then waiting for a response. If there's a timeout, so if they don't send a response within 200 milliseconds, then they would be able to return back and forth, back and forth. But usually it's you send 2 and then they send 2 and then you send 2. You don't really send back and forth, you send in pairs of 2 as an optimization. So that's one optimization. That's something that you'll see. And it's changed by the push flag. There's also retransmission. So retransmission is if you weren't actually, there was like a misparity between the sequence, the acknowledgement that you were given. Maybe you didn't receive something, and so you would have to continue requesting, and then the recipient says that you sent the same thing previously, so they would continuously send the last thing that they were to send. And you'll see this in Wireshark when we open it up, that sometimes you'll see TCP retransmissions, and it would have a certain color as well. So it's just saying that somewhere along the communication, a packet was lost or incorrect number of packets were given, and we have to send the same thing again. So again, we'll look at the TCP flags. The main ones are acknowledgement, which is used in the freeway handshake and also in sending things back and forth. There's also push, which forces an immediate response. So the thing where we send 2, so like we send 2 and then they respond after the second one. If you have the push flag, that ensures that you send 1 and then they have to respond immediately after. Our RST is used to reset a connection. SYN flag is used in a freeway handshake, and FIN is used to signal and terminate the connection a little bit more gracefully as well. Okay, so I think there might be, so we'll talk about Wireshark. Wireshark is a way to actually analyze the network traffic from one point of time to another. So we capture specific packets from one point in time to another, and you can record it and you can save it in a file. And you can use Wireshark to analyze these sorts of packet captures. So you can use TCP dump, or you can use Wireshark, or you can use the libraries to capture these packets. Wireshark is a tool to analyze these packets. So they would have different colors. The colors represent different protocols. So TCP is green, DHCP is blue, but you can change the colors while you're using the tool as well. And yeah, so there's some cool things that you can do. So in Wireshark, in terms of communication with TCP, it's a back and forth. You can actually see what's being sent back and forth. Actually, in this case, this protocol is HTTP, but HTTP is based off TCP, so it still has the same back and forth nature. And you can see how this looks like with a Wireshark stream. Maybe we have time. Okay, I don't know if we have time to actually open up Wireshark. Maybe we can do it afterwards if we finish early. You can also look at the protocols that Wireshark is setting up. So all of the protocols in your packet capture, you can open up Wireshark and see all of that. Sometimes it's good because you have protocols like RRC or very niche protocols that you don't expect that you can just take a look at. You are able to export objects. So sometimes you're sending files across the network. So Wireshark is able to look at the packets and then find out which ones are actually files, and then just extract it for you. And you can also do manual extraction by looking at the payload of the data. There's also filters. So when you actually capture a packet capture, you have a lot of packets. You're able to filter them with syntax like this. So you specify the protocol and a field of the protocol in header. So IP has the IP address, the source, the CRC, similar things in header. You would just set up these rules, and then it would only provide you the packets that match these rules. And yeah, there's also conversations, which are a way for you to look at what is actually being sent between IPs. So if there's an IP that's communicating with another IP at a specific port, you can see what's happening there. Maybe I'll skip this. This challenge is from a Swedish CTF that was happening last week. This one is kind of simple. How it works is that you're just sending a file. You're downloading a file from the internet, and you can be able to use Wireshark to extract that file. If you want to do it later on, you can take a look at that PCAP file. Okay, so we'll talk about memory forensics. This stuff is kind of interesting. It's not too in-depth, but it's kind of important. So when you are using your RAM, this is storing, well, in your computer, you have this thing called RAM, which is storing data that can be reset after the power dies. And it usually stores things about your programs, about the operating system, about most things that are being seen on your operating system. So it is connected to your CPU, but the devices like your GPU or your network interface or any single other device that you connect through PCIe is also able to directly communicate with the RAM with this intermediary chipset here. So the CPU is able to communicate with the RAM, but also your GPU, NIC, keyboard, other things are able to. Actually, I don't know if the keyboard is, but the GPU, the network interface, is able to communicate with the RAM directly. So what does the RAM store? The RAM stores obviously programs. It stores buffers, so things in your keyboard. It stores any opened files that are being written to. Stores connections, so you're connecting to something. There's a live network stream, and you're talking to it. It stores loaded content. So in your program, maybe you loaded an image. It stores that content, and it stores some things relating to the operating system for it to actually function. So in Windows, the entire registry or like a subset of registry keys are loaded into RAM, and one of the registry keys would be able to store the user's hashed password. And there are tools that would look at your RAM, and it would look at the registry key for your password, and it would be able to crack it. And this is what Mimikatz is. So there's a lot of very interesting stuff in the RAM, and a lot of things in RAM is decrypted, right? Because it's in use, essentially. So in terms of how memory is actually laid out, a program is going to be using different chunks of your logical hardware memory, right? Because maybe, for example, there are specific pieces loaded in memory, like libraries, that you want to use across different programs, like maybe a library to render things to the screen, like the Windows API to create objects on the screen. That is somewhere in RAM, so you don't want to continue loading that for every single program. So you want your program to be able to point to the specific segments of logical memory and then piece them together into virtual memory, which is a contiguous segment. So that's what virtual memory is, and there's a difference between logical memory, and you're going to be working with that a little bit if you do any deeper memory dumps. But we want the program memory to be contiguous, but it's not actually contiguous at the hardware level. Okay, so there's a really cool tool called Volatility Free that is able to allow you to analyze memory dumps. So how it works is that memory is just a collection of bytes, but we have tables that tell us, almost like structures in C, they tell us how we organize these bytes. So Windows has a lot of these symbols that are made public, and Linux has a collection of these for every single distro. You might have to make your own as well, depending on the configuration. But yeah, it's a really cool tool to analyze memory. We can maybe use it if we have some extra time as well. So you're able to install volatility like this. It's just a Python. It's just a Python script. But essentially, how it works is that you have a collection of symbols to patterns. You can use these patterns like Windows PS list, which is a pattern for the processes that are running. So you can input your memory dump, and you can input the plugin. So if I want to look at the process list, I say windows.pslist. It shows me all the processes that were running. Windows.handles, all of the handles that are open by the processes. Netscan for any network connections that were previously opened or are opened, and any keys in the registry that were left for the user. And the registry actually has a lot of really important information. Um, so yeah, maybe I'll upload the RAM dump later when it finishes uploading, but they're large files, so volatility would take a little bit of time to actually analyze them every single time. But once you analyze them, they're all cached. So I guess it'd be good. You have to do it on your own time, I guess. But yeah, okay. So we'll talk about logs and artifacts with the final section, which is if you are looking at a Windows system and you want to understand what actually happens, or you want to understand what the user did on a system, you'd be looking at artifacts. So logs are very descriptive artifacts. These are things that are created by programs or operating systems, and it stores interactions with the programs, it stores interactions with the operating system, and stuff like that. So logs are records of what has happened in a process in the OS. You can find them in folders. So Windows has all of the logs in the System32 Win event logs, and Linux has them in var log as well. If you want to view the logs on your system, you can open up something called Windows Event Viewer. Windows Event Viewer is this collection of all of the events created by your system. There's different types, so there's application logs, there's security logs, and then you can filter by the ID. So some IDs are relating to login. I think it's 4624 for login. So if you want to filter for all the logins, you can just filter through that specific ID type. So it's very good to see what's happened on a system before and what's happening on a system now. Something else that's really important for Windows is the registry. And so the registry really is the heart of Windows because it contains all of the configurations, or almost all of it, and it is written to while you're using a computer. So it is written into staging cache before writing to the registry, but some keys in the registry are also exposed. So what the registry contains are system configurations like your background, your username, your password hash, some things like maybe the game paths, like the paths of your games, the configuration of your games, if you're full screened, if you're minimized, some recent files, like your most recently used files. It stores almost everything about your system. So it's really important of an area of interest, and it's stored on the disk as well. So you're able to actually see where they are. The hives are the files that contain all of the configurations, and the configurations would be able to be viewed in the registry editor. So some of the common hives that you'll see are SAM for user account info, the username, the login times, the security for any policies that were set, software for computer software configs, so the software that you have by default and the things that you installed. There's a system for system configs, and then there's your user data for your wallpaper, your mouse size, things for customization, and then there's some backup ones as well. There's also some other files that are really interesting. So one of them is amcache. This is info about programs that have been executed before. So if you open up this hive, you can see all of the programs that were executed previously. You can see background process information, so any processes running in the background. You can see any processes relating to user settings that you're actually using, so that you're focused on. So this is the DAM. I forgot what it stands for. There's also shell bags, and these are info about the folders that you accessed. So there are so many of these things. When you have access to, let's say, somebody's hard disk, they made a copy of it, and you can see the registry. You are able to look through the registry and look for these things to see what programs have they ran, what folders have they accessed, and so on, and so forth. There's a lot more assets at this Try Hack Me link here if you're interested in that as well. I think the last artifact that we can talk about in Windows is the scheduler. So the scheduler is a way that Windows automatically schedules tasks. I think this is more useful if you're looking at malware. So a malware is able to set up persistence. That's one of the main goals of malware, is to set up persistence. So what you can do is you can set up a task, and Windows would be able to automatically run that program, or run that program at a given time. So those are scheduled tasks. So I think those are all the artifacts that we had to cover. Maybe we have time to look over a few of the tools. So maybe we can open up Wireshark, but that is everything we had to cover. If you're interested in trying out the challenges, there's a network forensic challenge online, and there's also I'll upload the memory dump later when I get home as well. So maybe I'll open up the packet capture challenge, and we can see how that works. There's a lot more things in forensics. There's disk forensics, which is looking at a copy of a disk, and then you can mount it and you can see every single file on your hard disk. And obviously the entire disk is going to be massive. It's going to be several gigabytes in size, but there's a lot of very important information, a lot of very important data that's on the disk, because you get access to all of the files. So yeah. So this is the PCAP file. And this PCAP file is actually not very messy. A lot of PCAP files, when you actually open them up, they're very messy because they have a whole lot of protocols, and a lot of them is just noise. Like, maybe I'll open up a capture. No, okay, we'll just go for this one. But a lot of the PCAP captures that you'll see, they have a lot of noise. I think they went into this file and just removed all of the redundant, unnecessary protocols. But so this is Wireshark, and you're able to see all of these packets that are coming in. There's not that many packets. There's only a set amount that are here. Some very good way that you can actually look at it is you have the frames. So remember how the packet is structured. You have the headers, and then you have the actual payload information that's encapsulated. So you have your TCP, which is at the lowest level, that's encapsulated by Internet Protocol, and that's encapsulated by the Ethernet. So if you were to actually get the data, you would remove the Ethernet header, remove the Internet Protocol header, remove the TCP header, and then you have the payload, which this one doesn't have, I don't think. Yeah, this one doesn't have it. But yeah, so where do we get started? We have to look at what protocols are being used. This is a very small one, so actually all of the protocols are TCP. So we can just look at the TCP packets. We want to see what's happening here. So I saw here, it looked like there was some plain text right here. So this is just a message to pp helm order something something, and this is in Swedish. This one's not really important, so I'm not going to read it because I already did this challenge before. This one's not really important, but this is something that you should document down. So if we go down a bit, you can see that this is very small, 66 in length. This one's 73, and in this, you see the payload is ls star star. So maybe they're looking for through the directory. Looks like they are. Is this solitaire? No, okay, this is something something else. From HQ, priority, scan PNG. Okay, so there's a PNG that's being sent back and forth for this solitaire. Solitaire command. Okay, that's weird. But we can go down. There is a RAR command, and RAR is a way to create an archive. So they're doing RAR, and then they're sending a password. PQAS. So we can copy printable text, I guess. Okay. But yeah, this is the command that they sent, rar ap, and then the file name is exfil.r, and then the file that they're adding is to HQ and from HQ, and the password is this. So we're just gonna save this password. Then what happens if we go down? There is this output of the help of rar. So I guess they did like the man pages of R. And then they compare it. So they run MD5 sum, which just checks the hash of the file. And I guess, yeah, so they just have the hash of the file here. What is really interesting, if we scroll all the way down, they download the file. And then you can see in the length field specifically, it's gotten a lot larger, right? Because everything up here was like 66, 112, but now you're getting giant packets being sent. And if you look at this payload, there's rar, which is actually a magic number for a rar archive. So this is the start of a file. So if I were to just copy the bytes, this would be a segment of a file. And the reason why it doesn't send the entire file is because it would be too big. So if you go down, this is another segment of the file. It's the second segment of the file. And if we go down to the next large chunk, this is the third segment, and it goes on for quite a little bit more packets. I don't think, yeah. Does it end here? It looks like it ends here. Yeah, so it looks like it ends here, or it could be here. Might be here. You have to look at the actual file format for RAR in order to know. Yeah, this seems like it's the final one. Anyways, because yeah, it seems like this is the final segment of the file. So in order to reconstruct the file, what you need to do is you have to extract the payload of all of these datas, and there's a command for that called tshark. Tshark is able to, it's a command line tool that you can use to extract specific segments of a packet. Okay, yeah, maybe I'll run through it. So there's a lot of things that you can do with volatility. It's a Python script, so what you can do is you can do Python free, the actual tools, so vol py. Yeah, okay. So vol.py, and you input a file, so memdump.mem, and then you input the pattern that you want. So if we want to see all the processes, you can do volatility-f, the file, and then windows.pslist, because this is a Windows dump. Oh, Windows, I see, okay. So if you've ever opened Task Manager before, you can kind of see similar things like SVC host, Notepad. So if you look at enough processes, you can find out which ones are kind of weird. So there's Explorer here. Explorer, I think this is the File Explorer, not Internet Explorer. There is DLL host to set up hosts. Explorer is also on Mac. I don't know what is what is Explorer? Because there's also the File Explorer that's used a lot. Oh, sorry, yeah, File Explorer, yeah, it is. This one right here. So it's being used. There's FTK Imager, which is to create a RAM dump. There's OneDrive, which is the cloud thing. So the main thing here was we can also look at whatever files that existed. File. I'll look through the previous commands. So you can run a file scan, and a file scan will look through any sort of file that was present on the memory dump. And there should be a lot. Also looks for registry. The registry contains almost everything. So it would look through a lot of this. A lot of this is Windows stuff. Yeah, most of this is Windows stuff. I think, okay, I'm gonna stop it. I have it saved already. So something that we want to look at is the user files. So we would search for users. There's app data for the apps that running. How many are there? There's more than 99. Maybe we can look for users and then documents. Oh, vbox user documents. Okay, so there's a download. There's a file in the downloads. There is a file in documents called supersecret.txt. So this is a file, and then we have the offset. So the very first thing is the offset in virtual memory. So we can copy this, and we'll save it in Notepad. Yeah, so we'll save it in Notepad. What else is there? There is desktop configuration, and there's a lot of things. So once you have all the files, look through the stuff in the downloads, documents, anything in the user area. What you can do is volatility. So we got this this offset in virtual memory, and that's a file. So what we can do is we can extract it. So we can do memdump. No, not memdump. File. Wait, is it memdump? Okay, I have to remember how to do it. Okay, it's dump file. So you're able to dump the file, and then what you provide is the virtual memory address, which is this. And then this writes it to a folder. And oops, wait, is this the right one? Where is our output? Okay, the output is dump. Okay. So this is the file that it created, and this is the actual content. So this is the flag if it was set up. But yeah, so you're able to use volatility to look at the processes, the files, like all the files that ran before, and you can use it to extract any files that are on the system. You can also look if there is like malicious processes like malware that was running. Maybe I didn't look into PSList that much, but in PSList you can see parent process, I believe. Volatility also has a built-in malware scan as well that I'm not really sure how to use it, but it exists to run a few checks against the entire processes and all the registry keys that are on the system. But yeah. Okay.